My dear students, our today's topic is about the quantum superpositions. The first question is that why we want to study this topic. The very simple answer is in order to analyze the superposition in quantum physics. For that we introduce the concept of this topic. In classical mechanics, superposition principle is very simple. Like for example, in electricity and magnetism or electromagnetism, if we are given with the two solutions of electric field, then the sum solution is the very easy case to be understood. But in quantum physics, it is quite strange. Therefore, we have to use the different approach in order to study the quantum superpositions. One of the best approach is with the help of a device, and that device is called Max-Zehnder interferometer. And the question that should arise, Max-Zehnder, in your mind is that why we want to introduce the concept of this topic. The very simple answer is in order to study the interference of two beams of light. But the question is, why we study the interference of two beams of light? Because the interference is actually the result of superposition. Therefore, we are choosing the interference because it is the result of superposition, and our goal and target is also the same, that we have to check or we have to analyze that interference pattern which is the result of superposition on the basis of quantum results. So now we have the experimental arrangement from the Max-Zehnder interferometer. The experimental arrangement is very simple here. We are given with the two beam splitters, two mirrors and two detectors in order to detect or in order to observe the interference pattern. So let's have a start with the sketch of that experiment. The sketch is in a sense that we have the beam splitter here. This beam splitter, the function of the beam splitter is that when you give the input, then this input is some of the part of the input is transmitted through this beam splitter, and some is reflected. This is called the transmitted beam and this is called the reflected beam. Here we have the mirrors. Here we have mirrors. This mirror is called M1 and this lower mirror is called M2. I should draw it clearly. Now, my dear students, when these output beams strike the mirrors M1 and M2, then they recombine at another beam splitter. Here we have another beam splitter. Let's call this beam splitter BS2 and let's call it BS1. Now, the interference pattern, because at this point here they will interfere each other, and this can be detected with the help of detector. This is the detector. Let's call this detector DO, and here we have a detector. Let's call this detector D1. Now, the very important point is that we have to clarify the concept of interference pattern, which is going to be detected with the help of detectors DO and D1 or D0 and D1. But in terms of photon, if you think in terms of photon, it will be very simple to be understood. Now, here we have the incoming beam, means the input beam. Think of the input beam as a sequence of photons. At a time, we have to send a single photon. But remember one point, that the interference, in this case, that the interference is not the interference of one photon with another photon. This is the very important point, that the interference is not the interference of one photon with another photon. must interact itself. Why? Because the reason is that we know that in destructive interference, when two photons end up, then we are given with none of the photon. That is completely impossible, because that would be against the law of conservation of energy. And the same is the case for the constructive interference. When the two photons ends up, then they should give the 4 photons. But that is impossible, because that would be against the conservation of energy. So therefore, the very important and the key point is that each photon must interfere itself. So therefore, a single photon is present in this beam and as well as in this beam. This is the very important point. So therefore, now we have to analyze that what will happen, or how we can use the quantum approach, what we will receive in the output, means through this detector. Either we will receive photon in the upper detector, or we will receive photons in the lower detector. The answer in the classical physics is very simple, that we can receive the photons in both the upper detector as well and as well as in the lower detector. Means we will obtain the intermediate result, the average result. But remember, in quantum physics, you will never obtain the average or the intermediate results. So now let's check, let's use the approach of quantum physics. Remember, in quantum physics, we do not obtain the photons in both detectors. Either the photons will be detected through D0 or that will be detected through D1. So now let's analyze these points. As we discussed in the earlier lectures about the states, like for example, in a very simple way, whenever we are given with any vector, a single vector can be written in terms of any 2 vectors or in terms of any other vector. Like for example, here is one vector and it can be written in terms of this vector here. A single vector can be written in terms of the different vectors. It is quietly similar in quantum mechanics, because in quantum mechanics we use the vectors, and that are not those vectors which are used in the classical physics. Here the vector means the states, and in the previous lecture I told that we have to represent the state with the help of this symbol and as well as with this symbol. This symbol is actually called the gap notation by Dirac, and this symbol is called the bra. And this notation is called bracket. This is called bracket. So these are actually the states, and I told in the previous lecture that states are actually the vectors. However, now consider it or think it as a state, that we can write a single state of photon in terms of any 2 states. Like for example, let's represent this state by A and represent this state by B. Now, if we want to measure any property Q of these states, any property Q means that property may be the energy, that property may be the momentum, that property may be the angular momentum. Whatever that property is, let's call that property Q. If we want to measure any property Q of these systems, like for example, if I want to measure any property Q of this system and I always get the result A, and similarly, if I want to measure any property Q of this system and I always get the result B. This is the very important point. If you want to measure any property, I told before that any property means that can be energy or momentum or anything else. If you want to measure any property Q of state A, and you always get small a, and similarly for B. Now, how to treat this with the help of superposition, or how I can write it in terms of the superposition principle. So here's I told that a single state can be written in terms of superposition of any other two states. Like for example, here we have a vector. This vector can be written in terms of any two other vectors. The same is the case with the states. A single state can be written in terms of any other two given states. Now here we can write it alpha A plus beta B. You can write it in terms of the wave function psi. Why I wrote in terms of the wave function? Because I told before that wave function actually determines the state of quantum system, or it describes the properties of states of quantum system. Therefore, I used psi, you can use psi as well. So now the very important thing is that what is the result of this equation? My dear students, the result is very, very simple. This result means that we cannot get the intermediate state in the quantum physics. Why? As I told before, in that case as well, that either we will get the beam here or we will get the beam here. Like in the experiment, either upward or downward, either in the upper detector or in the lower detector, we will get the photon. But it is not possible that we will get photon as well as here as well as here. So therefore, the intermediate or the average state does not exist in the quantum mechanics. So therefore, we have to use the approach of probability that was described in the previous lecture, and that lecture was the laws of determinism. So therefore, the probability to measure A is proportional to the square of alpha, where alpha and beta, my dear students, these approach to a complex number in generally. Now, the probability to measure A is actually proportional to alpha square, and the probability to measure B is actually proportional to beta square. So this is our today's topic. The very important and the last point that I should describe is the summary of the whole lecture. My dear students, the summary of whole lecture is that our today's topic was quantum superposition. Why we study this topic? In order to study the nature of superposition in quantum mechanics, which is quite strange as compared to the classical mechanics, and we have to study, or we have to describe this nature with the help of a device, and we called that device the Mach-Zehnder interferometer. And then we studied the result or the conclusion remarks that in quantum mechanics we always obtain a solution in terms of probability. We do not obtain the solution in such a way that there exists the intermediate or there exists the average result. The average and intermediate result does not exist. There always exists the probabilistic properties are the probabilistic results. You have to try the experiment, you have to do the experiment again and again, and then you have to analyze the results. So that is the very important point, and the conclusion of our today's lecture is that in quantum mechanics, the result which is obtained is not the average result, or that is not the intermediate result. So over tomorrow's topic, we will continue this topic more ever. Inshallah, see you in the next lecture.